So the Schrodinger equation looks something like this. I h bar partial differentiation of psi at a position r at time t with respect to time, which equals to minus h bar square by twice n Laplace operator square psi at a position r at time t plus the potential v at a position r at time t times psi at a position r time t. So this is our Schrodinger equation, and in this part we'll be taking v equals to 0, that is the potential is equal to 0, and the one-dimensional Schrodinger equation looks something like this. I h bar partial differentiation of psi at a position x, which is one-dimensional, along x direction, with respect to time t, which equals minus h bar square by twice n double differentiation of psi at x time t with respect to x, derivative of second order. So we have our Schrodinger equation in one dimension, the one-dimensional Schrodinger equation. So along the x direction, so before that, a plane wave has a form of a general plane wave is a form psi at a position rt equals a e to the power I k dot r dot product of k and r minus omega t, the angular frequency, times t. So along the x direction, k dot r dot product of these two quantities becomes k along the x direction and x along x direction, which we have kx, as here kx equals to k. So our equation in one dimension becomes psi xt position x and time t equals a e to the power I kx minus omega t. This is our equation, and from the de Broglie hypothesis we have p equals h by lambda, k equals twice pi by lambda. These are just the equations, and p equals h bar times k, and most important, E equals h nu, which is h bar omega, as nu is equal to omega by twice pi, the frequency. So from here and here putting the value of k from here, p by h bar, and the value of omega, this is e by h bar, in this equation, we get psi xt equals a e to the power I. In place of k, we write p by h bar times x, minus in place of omega, we write e by h bar times t, which gives us psi x t equal to a e to the power I px minus et, the energy, the total energy, et, divided by h bar. So putting these equations in our Schrodinger equation, one-dimensional Schrodinger equation, we get I h bar, differentiating psi, we get a e to the power I kx, sorry, not kx, we write this equation px minus et divided by h bar, and we have here minus e minus ie by h bar after differentiating, which equals to minus h bar square divided by twice m. Twice differentiation, we differentiate once and we have aei px minus et by h bar. Differentiating with respect to x, we get differentiating with respect to x, we get ip by h bar, this part. This is just simple differentiation, this part and this part. From here we see that minus I square, we get minus I square. We know that minus I square is equal to 1, is equal to unity, the complex. Minus I square equal to 1, and h bar here cancels out. We are left with this equation, which is indeed this, that is e psi xt, you can write this, equal to minus h bar square by twice m. Differentiating again, we get ip by h bar, and we already have this ip by h bar, which gives us the square, whole square, and this, that is psi xt. So here psi xt cancels out, h bar square cancels out, and the minus I square equals 1, already we've seen that, which gives us E total energy equals p square by twice m. So we have E equals p square by twice m. This is our final answer. So if you like the video, please don't forget to subscribe, share, like, and also comment in the comment section below. Thank you.